Hello and welcome back. In this session, we will go through the basic mechanisms of rock support used in underground excavations. In this session, we will learn the principles of rock support and reinforcement and the various rock support methods. As we have learned in rock mechanics, most rocks, except a few weak sedimentary rocks such as mudstones and shale, are stronger than concrete. For example, granite is typically 5 times the concrete strength or more. Therefore, in rock support design philosophy, rock is used as much as possible as a structural material, i.e., use the surrounding rock to be self-supporting. However, because rock mass around tunnels and mines are fractured and jointed, rock blocks will fall down. We need to make sure the rock mass stays as one big piece and not collapse and caving. That can be achieved by rock reinforcement. The most common reinforcement is using steel bolts to tie the jointed rock mass together to become one big continuous rock. We generally use the term of rock support to describe all types of methods used to stabilize the excavation in rocks. In fact, in rock engineering, rock support really means two approaches. One is to provide external support to rock. That is really the rock support. The other approach is rock reinforcement, as we just mentioned. Rock support is to apply external elements to deliver reactive pressure to the opening, roof, and wall. The common external elements are pillars of timber and concrete or steel, concrete lining, steel sets, wire mesh, and shotcrete. In old days, tunnels are supported by timbers and bricks. Reinforcement is a means of improving the overall rock mass performance by installing elements within the rock mass. It is similar as using the steel reinforcement in concrete to improve concrete strength and the resistance against tension. In rock mass reinforcement, we install steel bolts, anchors, and cables into the rock mass to strengthen the rock mass. We also shotcrete and cement grout to fill the rock joints and increase the joint strength. Here is a summary of different support methods can be used for different types of failures. Remember, we just learned different failure mode. Since support is designed against from failure, therefore, it is important for us to understand the anticipated failure mode and then design the appropriate support. For unstable ground of highly fractured and highly weathered rock mass, the excavated opening will not be able to stand without support. Therefore, we need to install full support quickly to prevent failure of the roof and sides, and even the face. In this case, the support is typically in the form of a structural ring of concrete or steel. For blocky rock mass, failure is mainly by the mode of block falling or sliding down. Therefore, Using rock bolts to tie the block back is the most effective method to prevent such a failure. Similarly, we have rock support methods for high stress-induced failure, such as spalling and bursting, and for squeezing and large deformation. We will elaborate more on those common and widely used rock support methods in the coming slides. In tunneling and underground excavations in competent and hard rocks, the most common failure is rock blocks and wedges falling from the roof and sliding down from the side walls. You have seen a couple of photos showing such a failure in the last session. The most effective yet simplest method is to fasten those unstable rock blocks by rock bolts. As shown by the drawing below, rock bolts are steel bars inserted in the rocks. They can be end-anchored, grouted, or use skin friction to tie the rock blocks together. By pinning those unstable rock blocks back to the solid rock mass behind, as we're seeing on the right figure, the blocks are stopped from falling and sliding. The excavated opening now is stable and will not suffer from any collapsing. Caving is one of the common failure of rock tunnels and caverns. Caving is due to the discontinuous nature of the rock mass, governed by the jointing and the fracturing. By systematically using rock bolts, we can build a continuous arch or ring around the opening, as seen on the right. This arch or ring is in fact a self-supporting structure because it uses the rock itself, but reinforced by bolts by fastening the rock mass together. This is perhaps the best example of rock support design philosophy we mentioned at the beginning of this session. Use the surrounding rock as much as possible as a structural material and to be self-supporting. The mechanics of bolt-rock interaction and formation of continuous rock arch or ring is illustrated by the diagram below. The dotted zone is the continuous zone reinforced by the rock bolts. For layered rock masses, by bolting the layered rock together, we can make a thick and continuous rock beam on the roof of the opening for horizontal layers, and rock pillar at the side walls for vertical layers. The mechanism is the same. Bolts fasten the discontinuous rock together and making them into continuous. Shotcrete is another most widely used method for rock excavation support. It is spreading concrete directly onto the rock surface to form a concrete layer. The sprayed concrete layer acts as support lining structure. It can carry shear and the tensile stress from the rock mass. Its load carrying capacity and the deformability improves when steel fiber are added. Application of shotcrete is quick, as it does not need formwork. It can apply to rough rock surface and flexible in size and shape. As shown by the illustrations below, the sprayed concrete layer forms a concrete lining covering the rock and stabilizes the rock. Shotcrete is usually used together with rock bolts and steel sets. As shotcrete is applied by spraying cement onto the rock surface with pressure, cement not only covers the rock face, but also penetrates into the rock mass and fills some of the joints opened at the rock surface. This effectively locks the rock blocks from potentially loosening and moving. This is illustrated by the diagram on the right. The concrete layer covering the rock surface also helps to prevent the deterioration of the surface rock. With the formation of concrete supporting lining and the locking of rock block movement, shotcrete is indeed very effective in stabilizing small rock blocks and wedges at excavation roof and side walls. By combining rock bolts and shotcrete, unstable large blocks are fastened by the bolts, and unstable small blocks are supported and locked by the shotcrete. Another form of support is adding a concrete or steel structure to support the pressure from the ground, to prevent collapse of the ground, and to bear high load in the ground. The support structure is commonly concrete lining or steel ribs, often in rings, as most of the tunnels are circular. Concrete lining and steel sets provide support pressure and limit ground deformation. As you can see from the illustration below on the right, ground pressure and deformation compress the supporting ring. The supporting ring reacts, provides the counter pressure. When the counter pressure from the supporting ring equals to the ground pressure, the opening stabilizes and the further deformation stops. We will learn more on this ground support interaction in a later session. For leveling and running grounds, such ring support is immediately installed after excavation to avoid any failure and collapse. For underground excavation suffering from very high stress, for example, at the great depths or in tectonic region, support is applied to take the high stress so the rock around the opening is not overloaded to fracture and to break. Rock bolts, steel sets, and concrete lining can be used as supporting element to carry the stress. This is illustrated by the figure here. The support must be designed to be sufficiently strong to bear the high stress. For underground excavation suffering from squeezing and large deformation, we will need to apply support to bear such large displacements. This is done by inserting support element able to deform substantially and at the same time to provide reaction pressure to control squeezing and large deformation. A variety of yielding support elements have developed and used in underground excavation and mining, including yielding steel sets and yielding bolts. Design of rock support for underground excavation is commonly based on rock mass classifications. Again, we use this Q rock support design chart as an example. The design chart gives different design requirements according to the rock mass quality and the excavation dimensions. In terms of spar bolting, systematic bolting with shotcreting, steel reps, and concrete lining. Those support requirements are designed for different potential failure modes that are governed by the rock mass quality. For example, at the right end, rock mass is of high quality and have only a few joints. The potential failure is by a few unstable rock blocks. Therefore, only spar bolting is required. On the left end, when rock mass is of poor quality, we're facing general failure of raveling, or suffering from very high stress or squeezing. Then steel rips and the concrete lining are required to provide heavy support. You have seen this figure in the last session, linking failure mode with rock mass quality and in-situ stress. Because support requirements are associated with failure modes, then again we can link support requirements with rock mass quality and in-situ stress in the same way as the failure modes. For good quality rock mass, shown by green, we expect the rock mass are generally stable with falling of individual blocks. Therefore, there's no need to support in general, but to apply spar bolting to individual blocks. But when good rock mass is under very high stress, shown by red zone, rock may suffer from burst and spalling. Support must be designed for high stress-induced failure. For poor and very poor rock mass, not subject to high stress, in the gray zone, then the failure is primarily raveling and running. It will require concrete lining to support the raveling and running ground. In the pink zone, when poor rock mass are under high stress, we are facing squeezing and need to install steel sets and the concrete lining. There are different approaches to design rock support for underground excavations. The main approaches are summarized here. Perhaps the most popular approach is to use the rock mass classification systems to design support. This approach is perhaps most suitable for generally competent rock masses with quality fair and above. We can design support based on strength and deformability of the ground, generally for poor to very poor rock mass quality. That is, generally for highly fractured and highly wise rock mass. Special designs for special rocks and special loading conditions, including faults in the shear zone, squeezing, and the swelling rocks, very high stress, and the very shallow rock covers. Rock support for underground excavation can be designed by a variety of methods, ranging from empirical to analytical and numerical. Rock mass classification systems are well-established methods for rock support design. The two widely used systems are Q and IMR. We will learn in detail how to use Q and IMR to design rock support for tunnels and caverns later. Assessing joint orientation and using projection methods to determine the potential of block and wedge fall and sliding can help to design spar bolting. To design concrete lining, steel ribs, and the pillars, we generally need to estimate ground pressure in order to design the support as load-carrying structures. For deep tunnels and mines, stress analysis must be conducted. Support design will be based on the amount of stress to be carried, and at the same time, opening shape may be optimized to minimize stress concentration and reduce the support requirement. Rock support in underground excavation are differentiated by temporary support and permanent support. Temporary support is the rock support or reinforcement installed to ensure safe working conditions during excavation or mining operation. Permanent support is the rock support designed and installed for the designed lifespan of the underground opening. For civil engineering, tunnels and caverns, typically their designed lifespan is 100 years. So the support is meant to be functioning for that period or longer. Support design we usually do are primarily for permanent support, and it requires to consider the stability and the functionality of the underground facility over a long period. The temporary support is usually part of the excavation activities, as it is mainly to ensure the excavation working can be safely done. However, much of the temporary support can be integrated into the permanent support. For example, bolts installed for temporary support can be functioned as for permanent support with proper measures for long-term use. This is the end of this session. Thank you, and see you at the next session, where we will learn how to design rock support. Bye.